We'll get started. I'll begin. Dear Father, we thank you for this day. Thank you again for these students. Just pray that you'd just guide our thoughts today as we study your creation, Lord. In your name I pray. Amen. Let me turn off this. I was going to turn off the fan, but we all know it's not possible. So here. Anyway, close this door. So when is our test? Next Thursday. When did I say it was next Thursday?
Syllabus.
It's in the syllabus?
The syllabus says the Tuesday, May 3rd. Or at least on math or super math. It says that.
What does it say? What does it say in the syllabus? It says, yeah. That would be the last day of class. See, I got confused. So there's something's got to give. Either I'm covering springs with friction, right, and the test is on, as it's stated on the course planner and on the syllabus, May 3rd, I believe, which is not next Thursday. That's actually the Tuesday. That's like what, 10 days from now or something, ish. Or I move the test up to next Thursday, but I'm kind of inclined not to do that because if you've been working off my course planner, then you're expecting the test was the last Tuesday. So I don't know, what is your, I'll open the floor for comments. Something's got to go. So what? Either remove the test or the final. I mean, I can get rid of both and just give you the average of your test grade so far. I mean, that's cool with me. There are like three people in here like, sure, I'll take that. Listen, I've been thinking about it. I think what's probably best for your education is if I leave the test on the last Tuesday, and that gives us you the most time to kind of absorb this material and get ready for the test and leave it where it is. And then on the other hand, of course, I should add some material. So, I should have some homework. The homework that's there is only on waves and simple harmonic motion. There's nothing on damping. And I think there are problems on damping in the book. So I could add WebAssign problems, but I just don't want to. So I think what I'm going to do is I'm going to actually make you a paper-based homework that you can write on a piece of paper and then turn in. And then a human will look at your answers and decide whether or not they're correct. I know this is weird, but I think we'll do that. However, those points will be bonus. So, yes. So I will give you bonus points. Although understand that material is not bonus material. It will be tested on test 3. But on the other hand, I think it's not difficult material. All right. The other reason I think I should do this is it occurs to me Dr. Wang is regularly teaching differential equations, and I sincerely doubt that he is commenting on the physical blah 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 of these equations that much, because he's not a physicist. And well, neither am I, so maybe I should just leave. But anyway, I have a little bit of something to say. Let me get to it then. All right, so test 3 is the last Tuesday of class. The final is the Friday of the same week. Yowzers. And but the final is just what? It's just the concatenation of, it's not literally cutting and pasting, but it is conceptually no different than test 1, 2, and 3 put together, right? And you're allowed four 3x5-inch cards for that final, right? They don't have to be the same ones you've used before. They can if you want, but that's the deal. Any questions about tests and such going forward? Yeah.
Are you still going to teach on waves and simple harmonic motion?
Teach what?
On waves and simple harmonic motion?
Yeah, I'm planning on teaching on, that waves and simple harmonic motion should come before damped harmonic motion, and that should come before, actually the damped and the simple harmonic motion should really come before the waves on the string discussion. So it's that, then that, then that. So, So, simple harmonic motion to start with, I suppose. So the quintessential example of this, of course, is what? Something like this, right? If you have a spring, this isn't quite right. If I was to do it right, I would have a spring, right? And then I attach a mass to it, and it goes, I'll see gravity is working its way on my demo. Oh well. This will come in handy later. So you gotta, here's the deal. A spring, it's attached to some mass, m. The spring has spring constant k, right? And I think we've talked about this before, but let's just start again. In equilibrium, right, there's some equilibrium x equals to 0. Equilibrium is when the spring is neither stretched nor compressed. So what's the force of the spring on the mass in that case? 0, right. And on the other hand, if it's like this, where's the force going? It's like this way, right? The spring force is pulling it back if it's stretched out. And so if you say that this distance here is x, right? So x, I mean, it's not distance. X is a coordinate, really, because it can either be positive or negative, right? And by the way, that question about why is counterclockwise versus clockwise, why is it a sense and not a direction, angered me. I have no earthly idea what the lab manual is trying to get at there. What's that?
It wasn't even in the lab material.
That's just total nonsense. Like, there's some sort of absolute difference between clockwise and counterclockwise versus left and right. Are you kidding me? Oh, well, right is always this way. Is it? I mean, what on earth was that question? I have no earthly idea. I'm sorry, yeah? I mean, you could say your right hand's always on your right, right? I guess there's that. I mean, is that the difference? I don't know. I'm pretty sure there's some molecule that's either like clockwise or counterclockwise oriented in some certain molecular sense. This is dumb. So I hate that lab book. All right, anyway, I digress. Getting to the point, Hooke's law, not mine, Hooke is minus kx. That's an experimentally determined fact. I think we'll check on that. Is it today? Today the...
Yeah, Stacy already.
Oh, okay. Hey, just like I planned. Well, maybe, sort of. Anyway, yeah. Okay, so you solve this, right? The point is, you have this mass, and we're assuming it's sliding without friction for the moment. And so what this gives you is mass times the acceleration is equal to minus kx. All right? So that gives me x double dot times m is equal to minus kx, or I could rewrite this as mx double dot, sorry, I just like to say double dot, plus kx equals to 0. It makes me happy. And that's a differential equation. Yeah. Yep. Second order differential equation, indeed. So this is x double dot plus k over m, x equals to 0. The solution to this differential equation is x of t is equal to some constant a, sine, cosine, what do you want? You pick it, cosine or sine. I'm going with cosine. No, I want sine. Sine, yeah, fine, sine. I don't know, it doesn't matter. Cosine of the square root of k over m times t, and then plus some phase angle, say delta. Here, a and delta are depending on, a is called the amplitude, delta you could call a phase angle. I'm not sure it's a standard phase angle. I don't know what's standard. Sorry. You can ask your engineering professors. Whatever. Anyway, there it is. And what does that look like? All right, so when t equals, I'm going to graph this time, and this will be x for the moment, all right? T equals 0, where is it? A, almost. It would be at whatever, this would be A sine delta, right? A sine delta, and then that's its like initial position, and then it waves, right? What's its initial velocity? What's the velocity of this spring? How about dx dt, yeah? So the velocity as a function of time would appear to be a, oh man, this formula is kind of a drag. Let's simplify it. Let's take this and rewrite it just a bit. I'm going to rewrite that as x of t is equal to a sine omega t plus delta. I'm introducing the angular frequency of the wave. Omega is the square root of k over m. I have more to say about that in a bit, but let me just finish this current thought about the velocity. So velocity dx dt, which is what? A omega, right? A omega cosine omega t plus delta. And then, yeah. So what's the velocity at time 0? Put t equal to 0 here. What do you get? You get a omega cosine delta, right? I suppose for what it's worth, on this picture down here, it's the slope of the wave as it crosses the x-axis there, right? What would happen if your initial position, right? If your initial position was a, what would that say about the velocity initially? In other words, sine of delta is equal to 1. What's cosine delta equal to? What's that? Is that here 0? Yeah, 0 is what I'm looking for. It's more obvious if you just think about it geometrically. A is the maximum length the spring is stretching, right? And then it compresses to minus a, and then it goes to a, and then minus a, and then a, then minus a. If you start with the spring stretched out and at rest, let it go, that gives you the maximum position. Your initial velocity in that situation is 0. All right? So, okay. So there's the velocity as a function of time, is this formula here, right? And let's see here. We could rewrite x in terms of its initial position and initial velocity more explicitly, right? Like, you could also, well, I guess I don't need to do that right now. I'll come back to that. But let's see here. What are other interesting things about this system that we would be interested in terms of the study of its physical motion? How about energy, kinetic and potential energy? What's the kinetic and potential energy here? If the force is equal to minus kx, and that's also equal to minus du dx, where u is the potential energy, as we've discussed before, that gives me u as a function of x is 1/2 kx squared, right? So what's u as a function of time then? What's the potential energy at time t? What do you do? It's not that surprising. You just take x, right? And you plug in the function of time over here, right? And that gives us a sine omega t plus delta, quantity squared, which is what? 1/2 k a squared sine squared omega t plus delta. Not an especially exciting formula, but there it is. There's the potential energy at time t. What's the kinetic energy at time t for our solution? What's the kinetic energy at time t? How do we calculate kinetic energy? Don't worry, this is not a relativistic spring. You're safe here. Oh, by the way, absolute sadness, I couldn't see the time dilation last time. I should have just drawn a line like this. I could have seen this was delta t over here versus the delta t prime was less, you know? So time dilation. If you look at a vertical line segment in the thing I drew last time, you could see it. Sorry about that. That was, oh well. Kinetic energy. Let me focus here. Let me put this relativistic half picture away. You are banished to the last class. Go away, foul sir. Ah. Getting back. What's the kinetic energy? 1/2 what? mv squared, right? How do I find the kinetic energy at time t? I could take the velocity at time t and just plug it in there. What do you get? A omega cosine omega t plus delta, quantity squared. All right, clean it up. This is 1/2 m a squared omega squared cosine squared omega t plus delta. All right, great. So the story goes, there's the kinetic energy at time t. Can we simplify this formula in any way? Now this symbol I introduced, the omega, what was its definition? Square root of k over m, right. So, yeah, omega. Let's see if we can figure this out here. So we had omega is square root of k over m. So omega squared is k over m, right? So 1/2 m a squared omega squared is actually just what? I think so, yeah. Yeah, the m's cancel. So we 1/2 ka squared, very good. Wait a minute, you mean to tell me the coefficient here and the coefficient here, they're the same coefficient. What's the significance of that coefficient? What should be the case? If we add kinetic energy and potential energy, what do you get? Total energy, right? Total mechanical energy. And what is that? I mean, I just showed you that this is equal to that, right? If I add these two things, I've got sine squared plus cosine squared, otherwise known as 1. So this is literally 1/2 ka squared. There you go. There's the energy of the spring. What else is it, though? That's the energy in terms of the spring constant and its amplitude. Can you tell me what the energy is in terms of its spring constant, perhaps, and its angular velocity? Its angular speed, its omega. Can you tell me that? You could trade the, we have what? K is equal to what? See here? I can solve that. That gives me K is m omega squared, right? So I could also say that the energy is equal to 1/2 m omega squared a squared, right? Yes, sir.
We're adding them together.
Sine squared plus cosine squared is 1.
It was like a 1/2.
Yeah, but like, well,
plus the 1/2 a squared.
1/2 blah sine squared theta plus 1/2 blah cosine squared theta is equal to 1/2 blah. Because we factor out the blah and the 1/2, and we've got sine squared plus cosine squared, which is 1. So, yeah. Excuse me. Oh, there's another popular way of characterizing the total mechanical energy of a spring in terms of the maximum velocity. What's the maximum velocity of the spring? Where's that going to... I mean, you can kind of see it. It should be at these points, right? There's the maximum compressing velocity. Here's the maximum stretching velocity. Compressing, right? Compression, stretching, out. I don't have a good word for it. What's the biggest V can be? Just look at the formula. What is max? What's V max? The largest the velocity could be is when cosine is 1, right? Cosine being 1, you get A omega. So I could also write this as 1/2 m V max squared, right? And there it is. It's like manifest right there. It's in your face. The kinetic energy at the case where x is equal to 0, all of the energy, kinetic, that's total energy, right? On the other hand, all of the energy could be potential, and that's 1/2 ka squared. Both of these extreme cases come together to give you the total energy. And then in between those two extremes, the kinetic and the potential is a somewhat complicated function of time. Not too complicated, they're just right there. But there it is. I guess I could rewrite this. Both of these coefficients, I could also just write what? E, right? If that's the total energy. Those coefficients are just E. You know, E sine squared or E cosine squared. But those are the energy. Yeah. And that's simple harmonic motion. So it's kind of an interesting story. It's all in this graph, really, right? In any given cycle, you have the maximum. You go fastest twice, either when you're on the way to compression or on the way to stretching out. Those are both maximum velocity points, and the spring is compressed the most here and stretched the most there, and that happens. So like the maximum displacement happens 2 times a cycle. And so you have this trading back and forth of kinetic and potential energy, right? In any given cycle of the spring, you've reached maximum kinetic twice, and you've reached maximum potential twice. So there's these 4 maximal points in any given cycle of the spring. And there's a nice picture of that in your book, right? In terms of these like little bars and things, if you look at it. Let's see here. There's more I should tell you, though. Some standard language. What's the period of the motion? We usually use a capital T for that. And omega is equal to 2 pi over T. So the omega, and so I guess you can solve for that. T would be what? 2 pi over omega, which is what? 2 pi square root of m over k. So there's the period right there. It's good. I mean, we could put numbers and things in, but I don't think it really adds much.
Why did you say omega is equal to 2 pi over t? Why did you say omega is equal to 2 pi over t?
Definition. I mean, logically it makes sense. The period should be how long it takes for this to get back where it started, right? So basically, you think about it, omega t should go to omega of t plus the period when omega t goes to omega t plus 2 pi. I mean, if you think about how this function works, it's 2 pi periodic, right? So that would give you the equation, if you compare these two, if you set these equal, that gives you omega t is equal to 2 pi. So omega t being 2 pi tells you that the period is 2 pi over omega, or vice versa. You can also write things in terms of like frequency, not angular frequency. And frequency is like cycles per second, so I think you usually use f for frequency. F and omega are related how? I think omega, yeah, or omega is 2 pi f, right? I think that's just what you said. I said it weird, but yeah. Right. So you also have that. And yes, and exactly the frequency, the number of cycles per second is literally 1 over the period as well. That's another relation that's known for wave motion. Okay, well that's the big story here. Now, simple harmonic, I mean, I have talked about simple harmonic motion in terms of a spring and mass, but you get this kind of motion whenever the differential equation you're studying basically looks like this. And this kind of differential equation comes up in other places. There are so-called physical pendulums where the same thing happens. In fact, I talked to you guys, or I think maybe Ms. Stromby also talked to you. I'm not sure. We should have talked to you in lab. I can't remember if I did it in class or not. Have I ever derived in class the similar equation for the pendulum? I don't see. I did it in lab, but I don't know if I did it in here. So if you have a pendulum, something like this, right? And, well, tell you what, I did this, I'm debating whether I should do it for the physical pendulum or for this ideal pendulum. I guess I'll stick with the ideal. So, of course what happens is, what happens? Gravity makes it swing and back and forth, right? Here, let me be less mysterious. Check it out. I brought toys. Don't get used to it. Stop. I said stop. Thank you. So a pendulum, right? And if you change the length, the period changes, right? Looks like if the length is shorter, the period is faster, right? See? Fairly long period, and then as I pull it up, the shorter it gets, the faster the period, right? Anyway, so why is that? Let's see here. Basically, I need to find the component of the force which is tangential. What is that? The tangential component of the force times the radius. I'll call L. L is the radius in this case. This gives me what? The torque, right? And torque should be equal to what? It should be equal to I alpha. Now, of course, in the case that you're just dealing with a simple pendulum, I is just mr squared. I mean ml squared in my current language. But if the pendulum wasn't simple, if it was some kind of blob, this would still make sense. All right, as long as I calculate the force on the center of mass, this would still be a legit equation. So what is that tangential force? Let me draw it this way. Here's mg, right? And, I'm sorry. I've made this picture hard for me to understand. It's because it's wrong. Okay. Let's try that again. Okay, so trying to draw it in the same situation as that one, more or less. So mg is like this. Here's the tangential piece, right? And then this over here is the centripetal piece, right? The centripetal force and tension are in equilibrium, I believe. Well, that's not true. They have to balance out to give you 1/2 mv squared, right? That just describes the circular motion. So, yeah, in fact, the centripetal part of gravity would not be equal to the tension. What we have is that the tension, right, which is which way? So here, you've got tension like this, right? You've got mg. This angle's what? This angle's theta down here, right? So mg cosine theta, you have tension minus mg cosine theta equals to what? This is going in a circle, right? So it goes back to that derivation we did early on. It has to be equal to mv squared over r. We're stuck with that. That's what the calculus tells us. So this has to be mv squared over, well, r here is L. Actually, that doesn't matter to us. I'm just saying it's there. I think I've already asked you questions about this in the homework, right? Oh, maybe that homework's not due yet. Doesn't count. I don't know. All right, so what's the tangential component to the force then, you guys tell me? mg sine theta, right? Sorry, I'm somewhat impatient. You got to tell me faster. L mg sine theta equals to I alpha. What is alpha? Alpha is theta prime prime, or theta double dot if you like. I know I like it. Theta double dot. Second derivative of theta with a function of time. Now this, and I'm missing, oh, there's a very important SIGN, right? I always make this sign error and then regret it. It's pretty obvious. Theta increases, right? If it swings this way. The tangential component of gravity, is it making theta increase or decrease? Decreasing theta, right? It's in the negative theta direction. So I'm supposed to have a minus here. That minus is pretty important. So if I solve this, right? Well, now I have to use a small angle approximation, right? That's the thing. Sine theta is approximately theta for small angles, right? And so that gives me theta double dot times I plus LMG theta equals to 0. And if I isolate my theta, I've got theta double dot plus LMG divided by I times theta equals to 0. Mathematically, that's the same differential equation, right? Like it's the same math problem. That is, see this right here? This guy and this guy, it's the same mathematical problem. They're really both generically of the form y prime prime plus, let's say, beta squared y equals to 0. They're both of this format. So anyway, the solution is theta of t is equal to some theta, let's call it theta naught. I guess we're using sine. Maybe I should call it like theta 1 or something. I don't know. Theta 1, sine of omega t plus delta, where omega is what? Where omega is the square root of that. So what's the period of this physical pendulum? So to a good approximation for small angles, the period of the pendulum is 1 over 2 pi, the square root of square root of I divided by LMG.
What constitutes a small angle?
Well, in calculus 2, we proved that within about 1%, sine theta is equal to theta, as long as you're within like 20 degrees.
20 years.
If you want better, you can go closer. So, I mean, basically the deal is sine theta is what? The sine theta is theta minus 1/6 theta cubed plus dot 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 dot, right? So the error in saying sine theta is equal to theta is about theta cubed divided by 6 by the alternating estimation theorem, or by Lagrange's formula for the remainder if you like. One of those. So,
Anything larger than that would have these kind of series.
yeah, I'm not sure how to do this calculation if I'm looking at large angles. I don't know. There's some way of doing it because there's a formula in the lab book. Of course, the derivation is suspiciously missing. I mean, what am I kidding? Just nothing derived in the lab book. But anyway, is there? I don't know. Maybe there is. I don't know. Anyway, this is a physical pendulum. If you put I equals to ml squared, that would be the moment of inertia for just like my yo-yo, where the string, I mean, where's the mass? It's the yo-yo, right? The string is nothing. So the moment of inertia for this is just whatever the length of string is that I have, and then times the mass of the yo-yo itself, length of this, m times L squared, it's just that. This I is more interesting if you were actually take something like, a ruler and like say drill a hole here and let it swing back and forth, right? Then you could have something like I is what? Is it 1/3 or 1/12 or what's that? 1/3 ml squared. I mean, so there are other cases where it's interesting, but if you put that in here, what happens? The m's cancel, one of the l's cancel, and you're just left with what? L over G, I think, right? Yeah, which you may remember that formula from the lab that we did, right? Okay, how did I solve these differential equations? I mean, sorry, let me just pause for a second here, think about my life. Yep. Ooh. Dinosaur. Sorry. Aha. Yes. We have now gotten to the interesting part. I mean, I think this is interesting too, but how did I solve this differential equation though, right? I mean, where is that coming from? And so the question I will ask and answer for you is, how do you solve second order differential equations? Now, if you had my section of Calc 2, this is old news. We've already covered this. I doubt Dr. Scombordis covered it. No. Yeah. But it's actually easier than the first order stuff. Because basically what you learn is that to solve a second order differential equation with constant coefficients, all you have to do, all right, is solve a quadratic equation. So here's the theorem. The solution of ay prime prime plus by prime plus cy equals to 0 is given by the characteristic equation. You have a lambda squared plus b lambda plus c equals to 0. So let's say that this has solutions lambda 1 and lambda 2, all right? So you can solve that quadratic equation in lambda. You get two things, lambda 1 and lambda 2. They could be complex, They could be repeated. That's cool. That's fine. There are answers. So case number 1, we'll start with the easy case. If lambda 1 and lambda 2 are real numbers and distinct, okay, then the general solution has the following form. Y is equal to c1e to the lambda 1t plus c2e to the lambda 2t. That's the general solution. That's it. You're like, don't you have to integrate or differentiate or something? No, you do not. You have to understand the theorem I'm telling you and apply it. If you take differential equations with me, I will derive this for you from an operator principle, or perhaps some other thing, but whatever. If lambda 1 is equal to lambda 2, all right, then y is equal to c1e to the lambda t plus c2te to the lambda t. All right. And then case 3, yes, there's a t here. I know, weird, but true. I'm going to make another thing over here, add a little bit of jibber jabber. And then the other case that's more exciting is when lambda 1 and 2 break into a complex case. So there we write alpha plus or minus I beta. It's a real, A, B, and C are real numbers. So the solution to this quadratic equation, they have to come in a conjugate pair. Pragmatically, this is when the algebra looks like the following. Lambda minus alpha quantity squared plus beta squared equals to 0. That's what would give me this. All right? But anyway, in that case, y is equal to c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. I hope you're enjoying this. This is the only time you'll see me say these things without deriving them. Pretty much. Because anywhere else I say this, I will try to derive these. But here, I won't. I'll just tell you these things are true, and that's how you do it. Simple as that. Why is there a C1 and a C2? Well, this is a second order differential equation, right? So in some sense, it's like you have to integrate it twice. So the C1 and C2 are the constants of integration. Physically speaking, they correspond to the fact that if you have a second order differential equation, you need both an initial position and an initial velocity to fix the motion. And C1 and C2 account for the myriad of possible initial conditions. There's a lot out there. Something really, really cool happens if we study the following problem. So what you're looking at m x double dot. A little preamble here. Mx double dot is equal to minus kx. All right, we talked about that already. Oh, I'll come back to that in just a second. There's one other caveat I should make here. Special case. What's a very special case of this? Yeah, alpha is equal to 0. Is that what you said? Okay, sure. Very nice. So y is equal to c1 cosine beta t plus c2 sine beta t. That's actually what we had. You can rewrite this as a cosine of beta t plus phi, or plus delta, as I was calling it. Oh, I did sine, didn't I? You can do that. That's just a relabeling of the C1 and C2. Like, if you expand this, what does this give you? It gives you a cosine delta sine beta t plus a sine delta cosine beta t. So by comparison, you can easily see that this C1 here is nothing more than that thing, and the C2 is this thing. So you have this freedom to rewrite your general solution as a sum of sines and cosines, or as a single sinusoidal function with an amplitude and an arbitrary angle. These are just two different ways to skin a cat. Either way, we come to the desired outcome. The cat's dead, just to be clear. Okay. Or suffering. I'll take that. No, I'm sorry. I want the cat to be dead. Let me not be a monster. Let's see here. I'm a monster. Sorry. All right. So that's somehow gets us to this case. What if there's friction? What if you take this spring I had drawn earlier and you stick it inside Jello or something, right? So you can imagine if you, I mean, this is still not the right thing. You need to, this is never going to work for anything. You need something like a bowling ball. That's still not right. You need something that can slide without friction along a surface, and then the spring is just pulling it. But then the whole thing is put in some kind of viscous medium, and it obtains a velocity-dependent friction force is what we solve. So like the simplest friction force you can think of is one that's just proportional to the velocity. So something like this, minus beta x dot. So this is friction. Oh, and beta is probably a bad choice here. Let me say B. B. That's a velocity-dependent friction force. Think about that. Does that make sense? As a velocity-dependent friction force, does that make sense? Force of friction. I mean, is the sign logical? What should we like for our friction force? So x dot is just a velocity, right? That's BV. Certainly, if we're going this way, the friction should really definitely be going that way, right? If that's not the case, we're in trouble. That's why this sign is here. So if you're going to the right, the friction force is going that way, and vice versa. If I'm going that way, the velocity is negative. That makes this positive, and it goes the opposite way. So this goes opposite the direction of motion, which is what I want. Okay, finally. So solving this, putting it all on one side, gives me mx double dot, right, plus bx dot plus kx is equal to 0. This is a second order, constant coefficient, ordinary differential equation. Also, you can prove that if these coefficients, like, of course, we're assuming what? M, B, K greater than 0, right? I mean, you could consider the case B is equal to 0. But if it's the case that all three are positive, that forces, in this laundry list of solutions, it actually forces the exponentials, like the lambda 1 and lambda 2 here, or the lambda here, or the alpha here. It forces those to be negative numbers. Let's see here. So what does this give you? Sorry, I gotta stick it up here for a second. It would give you m lambda squared plus b lambda plus k equal to 0, which I could divide by m. I get lambda plus b over 2m quantity squared is equal to k over m minus b squared over 4m, or lambda is equal to minus b plus or minus the square root of 4k. Oh, that should be squared. Squared, yeah. 4mk, yeah, thank you. 4mk minus b squared, all divided by 2m, yeah. And so that discriminant, the 4mk minus b squared, tells you the nature of the solution, right? So this would be like if 4mk minus b squared is greater than 0. This would be the case that 4mk minus b squared was equal to 0. And the third case would be the case that 4mk minus b squared was less than 0. Some of you guys want to be mechanical engineers, yes, no? Should be important to you. I mean, this is kind of like basic stuff, right? And I mean, why is this important? Well, if you're, for example, making shocks on a car, right? What is a shock on a car? It's a spring, right? And what do? You take a big spring and you shove it in a can of oil, basically, right? And the viscosity of that oil that basically controls the B up there. I mean, it's a little bit more complicated than this, but it's something like that, basically. And so you can, depending on how you have the shock set up, you can arrange for these different kinds of solutions occurring, basically. This first one is called underdamped. Wait a minute. Curses. I'm trying to think. This is critically damped. I know that. Critically damped. This, I believe, is underdamped. And this up here is overdamped. I think you'd like overdamped or critically damped for your springs, because that way, I mean, you definitely don't want underdamped, because then what happens? You hit a bump, hit a pothole, and we've all experienced this, right? The car just kind of goes vroom, and then it goes zoom, 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 and eventually it stops doing that, right? But you'd like for that not to be the case, right? So you're aiming for overdamped or critically damped, I guess, more so, right? You want to mechanically tune the springs to make that happen. Yep. How about some numbers? You like numbers? You're going to do something with numbers? Yes, I will. I will actually do something with numbers now. I will. I promise. Oh, good. We have time. Simple harmonic motion is this green case down here, right? That's the case that there's no friction. Is that physical? Is there such a thing as simple harmonic motion, or is that just an idealization? I mean, it's a pretty good idealization in a lot of cases. Oh, some of you are electrical engineers, yeah?
Yeah.
Same differential equation comes up in RLC circuits, except this is charge. And so you have like charge versus current, right? And anyway, a similar story is told. I think inductance is sort of analogous to mass. And I'm trying to remember. The B is like resistance, right? The B coefficient is analogous to just plain old resistance in a circuit. And if I recall correctly, the K is analogous to capacitance. So anyway, that's a story for another day. Don't worry, the rest of you don't have to worry about that until next semester, right? Okay, so where was I? Oh, examples. Suppose your mass is equal to 5 kilograms. Your damping coefficient is equal to 10 whatever. What should the units be on the damping coefficient? It should be like newtons, right? Divided by meters per second. And let's suppose that the spring constant is (15). Spring constant should have units of newtons per meter. Then and let's also suppose that x of 0 is equal to 10 meters and x prime of 0 is equal to 5 meters per second. Find motion. Find equation of motion. So I would encourage you to find a way to compress this into your formula card, right? You don't need all of it. After you work with it a little bit, there's actually not much here you need to write down. You don't need all of it. In fact, if you have one example of each case, that's probably enough. So this one gives me what? I get 5 x double dot, right? Plus 10 x dot plus 15x equals to 0. Let's make this simpler. Let's divide by 5. What do we get? I mean, you don't want to work with the 5, right? Divide by the 5. You agree? So we have what? We have lambda squared plus 2 lambda plus 3 equals to 0. Oh, man. Did I say 15? Fine. I'll take my medicine. Lambda is equal to minus 2 plus or minus the square root of 4 minus 12. I'm sorry, I can't even do the quadratic. You know, I've gotten to the point where I can only complete the square. I'm sorry, it's a vice I have, but lambda plus 1 squared plus 2 equals to 0. I just see that to me it's just simpler to do that. I don't know. You guys can do the quadratic formula if you want. I'm not. And so I get lambda is equal to minus 1 plus or minus the square root of 2. If you believe me, those should both be negative. Are they? What? One of them's positive. Huh? That's not cool. Oh, I'm an idiot. You're like, we knew that already. Hey, that's not nice. Be nice. So lambda is equal to minus 1 plus or minus I times the square root of 2. I was just making the point over here that if you complete the square and it comes to something like this, a sum of squares, that tells you it's complex. And you can read from this alpha is equal to minus 1 and beta is equal to root 2. Consequently, x of t, and you got choices, right? You can write it like this, guys, or you could write it like this. What do you think we should do? What would be more convenient for the purposes of this problem? I think the C1, C2 would be easier to work with here. Let's go with the C1, C2 approach. C1 e to the what? Oh, minus t cosine root 2t plus C2 e to the minus t sine square root of 2t. Now we got to figure out what is C1 and C2. How do you do that? Well, x of 0 is what? Well, I guess I need to figure out what x prime is. X prime is awful. Let me cut my work in half. If we plug in 0 first, oh, that's no help. Did I say 10 meters? I meant 0 meters. There. Life is better. So x of 0, only I'm allowed to do that. X of 0 is equal to C1 plus C2. Oh, that's not true. What's sine of 0? That's 0. This is 1. That's 1. So we just get C1. C1 is equal to 0. Well, that's nice. At least this piece is gone. All right, so what's x prime of t? It still requires us to do the what?